Perfect. Okay. In that case, it's time to start the first official paper session. The first session is entitled Performance Analysis and Optimizations, and the first paper by Laura Promberger is entitled Assessing the Overhead of Offloading Compression Tasks. Laura is actually a second-year PhD student who has a dual affiliation with CERN and the University of Heidelberg, which is an absolutely beautiful university if anyone's never visited. Her working group at CERN is the online group at the LHCb experiment, and her research topics include the analysis of compute, storage, and throughput trade-offs of high-energy physics and data acquisition systems. So we will have a 5-minute pitch plus 10 minutes of additional question time. And this is Laura's pitch slide. So Laura, if you're on, feel free to begin.
Yes. Do you hear me?
Yes, yes.
Okay. Thank you for the introduction, John. So the work I'm presenting here is on the assessment of the overhead of offloading compression tasks. Nowadays, there are many different accelerators available which allow the acceleration of all kinds of tasks. And in this work, we have a specific look at the commercially available compression accelerators and how well they perform in comparison to compression algorithms run on the CPU. For this, we put a focus on the comparison between the CPU version CLIP level 2 and the accelerator, as both use the deflate algorithm and both had a similar compression ratio. For the evaluation, we used multi-threaded benchmarks, which we tried to keep as similar as possible to reduce the bias introduced by different implementations. We also utilized NUMA binding to get a better and more consistent performance. Our benchmarks, we run both with well-known compression corpora as data input and also with the for us relevant high energy physics data. The analysis showed that when running the accelerator, the memory bandwidth and the power consumption was stable independent of the dataset used. Also, the throughput was quite stable with only 7% variation between the datasets, while the CPU-only algorithms had up to 42%. The difference you see on the plot, which is in the middle at the upper part, with the two colors, with the red for the CPU, only best throughput, and blue the accelerator. The required memory bandwidth was around 80% of one socket, so that the best collocation CPU workload would be one which needs a lot of computation power, but at the same time needing a low memory bandwidth. We believe that commercially available compression accelerators are a realistic option to both benefit from accelerator advantages of having a high throughput and a low power consumption while keeping the investment cost low. However, one has to be aware that the host resource requirements are not neglectable. Furthermore, this work can be used to select the right compression algorithm for a given task, as it was shown that the algorithm's relative performance was data independent. Thank you for listening, and I welcome any kind of questions about this work.
Excellent, thanks, Laura. Are there any questions? So I actually had a series of questions. So in terms of the platforms that you've tested on, have you tested on any platforms with the latest AMD processors?
Yes, but this is ongoing work right now. So right now I have what is this? The 64-core EPYC Rome Zen 2 architecture, a dual socket one with 256 gigabytes of RAM. And for this, we are currently doing analysis on how the accelerator performs when we have in parallel different kind of CPU workloads running. And we hope based on this that we can kind of give a general recipe or policy what one should consider when working with that kind of compression accelerator to get a good performance for both the accelerator and for the CPU workload.
Oh, interesting. Yeah, we are actually doing some research with something slightly different. It's actually an RPC package from Google called gRPC, and there was recently a series of performance threads on the mailing list regarding actually the AMD Rome processors and the way that the core numbers are interleaved versus how they're interconnected to the PCI Express buses.
Yeah, we also had some interesting research with that.
Okay, yeah, that's what I was interested. I'm especially interested in that because it's very different than the way they were previously configured and the way the Intels are configured. So
yeah, so this is not really related to my work, but in our group, as we need like the 400G or the 200G maximum stuff with all the 8 PCI slots we have in the server we are having. There had to be done some tricky combination as the PCI slots are not interconnected, how it would look in a normal way. I think some of the PCI slots are switched and connected to different sockets and not in the same order. And also then depending on to which part of the socket they're connected to, they can offer a different amount of throughput.
yes.
So if you need something like this for the maximum, I could maybe ask in my group if they want to share the research.
Perfect. Are there any other questions from the group?
I actually have a question here. So actually for the benchmark you are mentioning, I think you're mainly working on FPGA architecture. I'm not familiar with FPGA, but I'm interested in the other accelerators like GPU. So are you planning to extend the benchmark to also covering other accelerators, or it's just the main design of FPGA?
So the thing is that we want to have an accelerator for compression where we do not have to implement so much on our own, because all our other resources are busy with developing other part of software. And that's why we looked at commercially available compression accelerator. And the problem with GPUs is that in theory, or the thing I have seen so far is that they're not very efficient for compression because you have a lot of data transfer, and contrary to good GPU workloads, we cannot keep all the data on the GPU to do our calculations. Instead, it's like we have a constant flow of data and not much time which stays on the GPU.
Yeah, that makes sense. So are you, apart from FPGA, are you aware of other like reconfigurable architecture that can be used for efficient compression, and that may be like and maybe included in the benchmark so the others can use it to test?
So we tried to look at the Intel Quick Assist, which is an ASIC, kind of like a fixed FPGA. But the software Intel provided was not very stable to communicate with the accelerator, so it was rather frustrating for us, and we decided to not continue putting there any more work into it.
Yeah, makes sense. Thanks. It's interesting. Yeah, work. Yeah, I'm not sure if everyone else can just turn off their can unmute by themselves. So if someone wants to try to unmute and ask a question, but you cannot, please send a message on Slack so we will fix it.
Okay, perfect. If there are any other questions, as Min said, please post them on the Slack channel, and we'll make sure and circulate everything. So the next talk is entitled "Improving the Space-Time Efficiency of Matrix Multiplication Algorithms." I don't believe Jan was going to be able to make the session here, since it's quite late for him in Beijing. but we want to at least mention that he did have a paper. There is a paper accepted, and hopefully we can get things worked out with all that. I believe the slides are, if not already posted, will be posted soon on the P2S2 website. So with that, that actually brings us to our break. We would normally have a break from 1:10 to 1:30 EDT, but in this case, we're going to wrap up for a break slightly early, but we will be back to begin the second invited talk by Sunita at 1:30 EDT. Min, would you like me to leave the slides up?
Yes, please. So probably we don't have to share slides from now, but yeah, I think it will be after 30 minutes. We'll be back online and continue the session. And for now, I can share this screen. So John.
Okay, I'll stop sharing.
Okay, thank you. So let me share my screen. Just everyone knows what will be the next session starts. Okay. So can everyone see my screen?
Yes.
Okay, perfect. So let me move to the next session. Okay. So yeah. So this session will start from 1:30 p.m. EDT after 30 minutes after now. Okay. So yeah. I will stop recording for a moment and restart the recording when we restart it. Recording now.
Okay.
So for the new attendees, I want to let you know this. We are recording the video and we will post the video, the live session to their website along with the pre-recorded presentations. So now it's on. Okay. So Sunita, before your talk, I would like to have like 1 or 2 minutes to brief introduce you. Okay.
Okay, sounds good.
Okay. Yeah, I think we'll get time now, and we are getting more people coming from back from lunch or break. So let me start the next session. So the next session will be an invited talk by Professor Sunita Kandarasekaran. Sunita is an assistant professor with the Department of Computer and Information Science at the University of Delaware at USA. She received her PhD in 2012 on tools and algorithms for high-level algorithm mapping to FPGAs from the School of Computer Science and Engineering, Nanyang Technical University at Singapore. Her research spans high-performance computing, parallel programming, benchmarking, and data science. Applications of interest including scientific domains such as plasma physics, biophysics, solar physics, and bioinformatics. She is a receptor of the 2016 IEEE CS TCHPC Award for Excellence for Early Career Researchers in High-Performance Computing. Sunita has been involved in the program steering and organization committees of several conferences and workshops, including SA, ISA, IPDPS, and so on. So let's welcome Sunita to give us a talk today on the programming models for the next generation systems. Okay.
Thank you. Thank you everybody for hosting this. It's a challenge to do this online. So I highly appreciate you folks developing this, whole program and enabling the platform and making this happen. So kudos to all the organizers and thank you very much. So this talk, I'm going to talk about a couple of case studies, but I'm flexible with the time. I know it's like 30 minutes. So feel free to, show me a hand or, a chat if I've gone over time, I'll definitely try not to. The way I've structured this talk is to give, to discuss a couple of case studies and how we are approaching the problem today with the current platforms, and how we plan to approach the problem for future platforms, and what would be the issues, challenges, and how do we plan to overcome them. So I will be able to tell you all that is not under NDA, which was a bit of a challenge to frame this talk, but I do want to tell you, what are the issues that we are facing. Just to give a perspective that, architectures evolve, things change, and we have to keep preparing for the next generation system constantly. So first up, thanks to my wonderful group. So that's during COVID times. So this research group meeting over Zoom at different times. So that's how we have been surviving this past semester over summer, and we will continue to do so going forward. So I wanted to start off with this intro slides. I'm pretty sure I haven't covered all of the programming abstractions, and the sizes of the boxes as it grows is not intentional, it so happens to be that way. But if we were sitting in person, I would have loved to have a, show of hands as to who is using what, right? So we have a number of opportunities and a number of ways to program heterogeneous systems. Several of us use several different, programming strategies. So some use libraries, some use abstractions. My group predominantly works on directives, and we on and off use, CUDA programming frameworks, and there are several others that are coming up as well. And this is not the end of the software pipeline, right? There is more to it. So we have different ways to program, and there are different pros and cons for each method. So I'm mostly going to tell you what has worked and what hasn't worked with both abstractions as well as directives. Although we haven't used Cocos and Raja, but a different kind of a programming, C++ programming abstractions that you will see in a bit. This is probably a familiar development cycle. You take a code, you analyze the code, you profile the code, try to find out hotspots, and then you try to see, which parts of the program you want to parallelize. Most of the times we are not happy with the first round of parallelization. We go back to the drawing board. We reanalyze, we reprofile, and try to figure out where else can we crunch, more data, more performance. So the cycle keeps going, right? Oftentimes in my group, I'll have to tell the students to stop. Let's move on, because you keep, trying to squish as much as performance as you can, and you can keep doing it because it's a never-ending problem. One of the case studies we got was we managed to reduce, a lot of time taken, about hours, 15 to 16 hours of a program in single core, to a few seconds in a single GPU. And even within that 46 seconds where we brought down the optimization to, we could have gone down to 20 seconds, 15 seconds, because the rest of the time was IO. But that's when I had to stop them and tell them, move on. So, you can keep doing this, right? There's a wonderful cycle that we refuse to come out of. So that's a crux of what the development cycle typically looks like. What I want to talk to you about is one of the exascale projects that we're involved in, where the goal is to prepare a plasma physics code for the next generation hardware. So what kind of software stack do you need? What do we have today? What kind of migrations and updates do we have to do to the software stack to get the code to work on the next big system? So that's the major exascale project that we got awarded last fall from Oak Ridge Lab. So this is the CAR project. CAR stands for Center of Acceleration Application Readiness, where Oak Ridge, every time when they have a big system coming in place, they select a handful of teams. For Frontier project, which is the next upcoming machine at Oak Ridge, they selected 8 CAR teams. So our team is one of the 8 CAR teams where the focus is plasma physics, P-con GPU, and how to migrate P-con GPU to Frontier, and how can it help advance the science of P-con GPU by being able to simulate, faster and more simulations on a bigger system. So as you can see, there's a bunch of names. So it's a massive project, you know, it's across the Atlantic Ocean. So we collaborate with the HCDR and CASUS, who are the centers in Germany, Oak Ridge Lab, and we have collaborators from Georgia Tech as well. I have a PhD student that's working on this project. So the long and the short of it is preparing P2S2 GPU for Frontier. And this is work in collaboration with Center of Excellence, AMD Cray developers as well, who are building the Frontier system. And you see the term Alpaca. So that is the programming abstraction that we use for this particular P2S2 GPU plasma physics code. And Alpaca, I'll tell you a little bit more about that in a minute, but it's a template-based C++ programming abstraction. I wouldn't call it similar to Cocos and Raja because the Alpaca group wouldn't agree to it. But that's the HCDR team back in Germany that has been building Alpaca, abstractions. P2S GPU is basically written in Alpaca, using Alpaca abstraction. So what can the code do, right? In the grand scheme of things, there are several applications that the code P2S GPU can be used for. One of them, for example, is suppose chemotherapy, right? So you need really sharp laser beams that can only kill cancer cells and not the healthy cells. When the healthy cells get attacked, that's when the side effects becomes more and more, and we don't want that. So how sharp or how accurate can the laser beams be in order to make sure that in a biology experiment, for example, chemotherapy, we can make better impact on the whole process without making sure that the healthy cells are not damaged. So that's one example. Another example is to study physics, to study matter, to study the properties of matter. And to enable to do all this, we need we need those laser sharp laser beams, and these beams can be at electron voltages from multi to tera electron voltage. So again, the possibility of going up to tera electron energy is still being explored, but by performing many simulations at higher end with Frontier, we will be able to achieve, some or at least closer to that of tera electron volt electron energy capacity. So that's the overall idea of why P2S GPU matters, or what do we want to achieve with the P2S GPU code. Now, this is the Alpaca abstraction. So like I said, it's a C++, based on C++ 11 standard. And the idea here is maintaining performance portability, which means Alpaca can have multiple target backends, basically. So I don't know if you can see my mouse, but if you look at the offload purple box, you see underneath NVIDIA GPU, AMD Xeon Phi, and you have different programming languages. So Alpaca allows you to compile and retarget using a different backend on the kind of system you want to target. That's the reason why we stuck with Alpaca. Now, for example, P2S GPU was a runner-up for 2013 Gordon Bell Award. So at that time, it was AMD and NVIDIA GPUs. So Alpaca's backend were AMD CPU processors and NVIDIA GPU, so CUDA backend, for example. So you can select and configure the backends you want. And there are multiple backends available, and you can choose the one you want at the same time. So there are several features of Alpaca. One of them being with Alpaca, the burden, or I shouldn't call it the burden, the onus is on the programmer to decide how you can move data between the different memory copies of both CPU and GPU. Now, with my directive hat on, I would say, so this definitely asks the programmer to be much more skillful to be able to move data between the different devices. At the same time, by allowing that possibility, you're not creating a software stack that is closely associated to your data structure, which means you can move things around as you want at the higher level and be able to target more than one type of platform. So there are pros and cons depending on what hat I wear. But when I look at Summit and I look at Frontier, we are already seeing two different machines with different capabilities, different architectures. So in that aspect, having written code for one type of system and being able to move from A to B without touching the code doesn't make sense, right? Because you have a totally different system in place with respect to Frontier. AMD GPUs are significantly different to that of NVIDIA GPUs. So, so pros and cons with Alpaca, and that's precisely what we are trying to figure out at the moment, that whatever worked on Titan is kind of working on Summit, but what else do you need to do to the Picon GPU Alpaca code base so that we move, Picon GPU to Frontier, which means we have to test on baby Frontiers, just like there was, Summit Dev. There may be Frontier Dev, which means, preliminary versions of AMD CPUs and GPUs as test platforms to see how the code is going to perform on Frontier systems. So we have several Alpaca test codes, because every time you cannot really use the entire 80,000 lines of code or 50,000 lines of code to test a particular feature. So you write mini test codes and stuff. So these are some there's two of several plots that we got from Nsight on Summit. This is the runs of one of the 3 compute-intensive Picon GPU kernels. This particular kernel is compute current kernel. Nsight, if you have used, it's kind of similar to NVProf, but you're getting more like roofline model. You get an Nsight, which you don't in NVProf. So these are some of the plots that you may also see in NVProf, but as you know, Nsight is the the new NVProf, if you like. So here we see GPU utilization percentages. So you see if the code is compute bound or memory bound or where the problem is. And you have several other graphs which tells you shared memory usage. Here, this particular graph tells you block sizes. What is your maximum block size that you can afford, which will give you the most warp occupancy. Warp is 32 threads, an NVIDIA GPU, in AMD it is 64. They call it wavefront. But so these are the kind of plots that you see with Nsight. So you can go back to the code and do some more experiments to see what can be your block sizes to get the max warp occupancy. And this is just one of the several tweaks you can do based on code analysis, which is why in my development cycle, I was saying that it's a cycle because you profile, you analyze, you optimize, you go back profiling. You have done it many, many rounds to be able to arrive at the most optimal code, if you like. So this is on Summit. It's called Figure of Merit, where the entire Picon GPU code runs on Summit, and for which we had to get full access to Summit. And the metric for Picon GPU is tera updates per second. And you see there is a formula based on the science part of it as to how you calculate figure of merit. The goal being on Summit, if you can achieve 14.7 tera updates per second, how far can you go on the next big system? So it's kind of a benchmark, if you like. So we had to make sure that our benchmark is a good enough benchmark, that we want to hold on to, so that when we run the code on Frontier, we are around the ballpark figure of 14.7 tera updates per second. So this is for a certain size of Picon GPU. So there is, of course, the weak scaling and strong scaling. We did those runs as well. You see certain dips there, which we are trying to figure out with Oak Ridge as to why. Could be because of MPI communication overhead, or it could be something else. And since it involves the full system, this is one run. So when you do several runs, you're going to get an average out of it, which is typically acceptable. So this hasn't been run several times, so that is another to do. But so that's a benchmark, if you like, on how the code performs on Summit. And I wanted to show you folks this because you don't need a Summit account to get an idea of the visualizer of the Summit node. I found this very intuitive. And I was teaching this in class to the students and stuff because this is apparently developed by an intern in Oak Ridge. And this is such a valuable tool, which kind of tells you when you slap the code on Summit node, one single node, how the node is occupied, right? So here for base, and you can, I believe you can look up the link And there is a little box in the left-hand side where you can just submit a job script, just like you would use in any other system. And you can play with the different boxes when it changes depending on your job script. So here, for example, at the top row, you see 0 to 5, which are 6 GPUs on the Summit node. And it has 44 IBM cores, but 4 are for other purposes, and 42 cores are the ones that are active at a time. The one in the bracket is the thread. When you see 0 and 0, the outside one is an MPI task. The number inside the bracket is your one thread. So why, if you think they're all over the place in a cell of 4, in a matrix of 4 cells, is because hyperthreading. So if you turn on hyperthreading 4 cores, all the 4 cells are going to be activated. So you're going to see all the 4 cells occupied. So just basic idea, I'm not getting into the details, but recording is available. I'll post the slide as well. So there's a JavaScript example, which kind of tells you how one node is occupied in a Summit node, which has 44 IBM Power cores and 6 NVIDIA V100 GPUs. Now, all this looks wonderful, or looks okay. When we move to Frontier, the question is, we need to repeat all of it. This is what led me to call the talk title as an opportunity or a nightmare, because we are somewhere at the borderline at the moment. We are wondering if it is an opportunity or it is a nightmare, because we have to look at a very different beast, right? It's a very different system. Titan to Frontier was okay, not too bad. But Titan to Summit was not too bad, but Summit to Frontier is different. So we are starting to build backends for Alpaca, includes HIP backend, OpenMP5 offloading, submitted a ticket to create a particular feature in OpenACC. And the process entails, you come across a bug, then you report this to vendors. Vendors test it out, they post a new version, you go back and test the version, you see if it works, if it doesn't work. So there is a ton of process in the background, right? And we work with different vendors, and we work with the AMD Cray developers, which is a COE team. Then there is the OpenMP community, and then there is the OpenACC community. And then there is Alpaca itself, for which we are developing all these different backends. And like I said, you don't want to be using the 50,000 lines or 80,000 lines of Alpaca and P1 GPU code every time. So we're creating mini test codes, or Alpaca mini test codes, that we use to stress test different compiler versions and the different hardware architectures we have access to via the COE. So while I cannot go into specifics, few things that comes to mind is, is the memory availability on the GPU good enough? Right now with NVLink, your 32 gig is your max in the GPU memory capacity available on an NVIDIA card. Now, is that good enough for the kind of test cases that we are testing? And today in the morning, while I was looking through my Twitter, I came across saying with PCIe 5, NVLink is going away. So that's new knowledge, right? So things change. As you're planning your backend platform, things change as we speak. That's how architectures evolve. So how close are we to getting our software ready? So that's what the car project is all about, right? So this is exactly what the project is supposed to do. Find out the nooks and corners, find out what needs to be done to get code to work on the next big system. So the process is 2 years before, even the system is not even there, right? It doesn't even exist. We're starting to already work on the software stack, which is how it's supposed to be. So there's active work going on. We haven't published any of this, as you can imagine, but there is more work to be done with respect to OpenMP5 offloading. A lot of test cases, a lot of things happening in the background, but hope to get there. We have to get there. So, and there's another project which syncs up very nicely with the car project, where here, this is a project which builds offloading test suite for OpenMP 4.0 and above. So it's a validation and verification test suite. With the Frontier machine coming up, OpenMP is one of the most important on-node directive-based programming model. So we need the compilers to be in a robust, matured stage. How do I ensure they are in the robust, mature stage? So this is a project, it's an ECP Solve project. Solve project is massive, so this is a component of the ECP Solve project. I work with Oak Ridge and my group, where the long and the short of it is, read the compiler specification book, which is of 600 pages. So you look at a particular feature, you figure out what the feature is talking about, you write a test case, and you test your case against available offloading compilers. If it works, great. If it doesn't, go back and find out if your test is a problem, or if the compiler is a problem, or if the specification is a problem. Could be any of those. And I'm going to tell you that more in a little bit, but these are the people who are currently using the test suite. We are testing using our test suite on Summit and Berkeley Labs, Cori and Perlmutter. But the vendors themselves are taking the test suite and running nightly builds on their own systems. And so this is what I was telling you about, right? You take a specification feature, formulate the test, discuss validity, adherence within our group, because if you make a GitHub commit, you're not supposed to merge it. Somebody else has to review your commit. That's rule number one, right? So whether it's one person writes, one person figures out if the test is written correctly or not, we agree within the team. The test goes to the test suite, saying that we know we created a valid test, but suppose the compiler fails, then we are back to the drawing board, right? So if the test doesn't pass, we go back and scrutinize the specification, we go back and scrutinize the implementation, then we go back to the vendor says, oh, your test is not written correctly. Then we go to the specification, they say, oh, specification is correct, go back and redo your test. So we do all of that, and then we argue the test is fine, your compiler is not running it correctly. So it's good to have more than one compiler to test, because then you can know if your test is written correctly or not, if multiple compilers behave differently. So it's always great to have more than one compiler to test. A very simple example of what works and what doesn't. So again, if we were sitting in person, I would have asked a show of hands as to which is the right version of the code, right? And this goes back to reading the specifications. There's two blocks and you have an array size. One is divided by 2, one is int. You're using a map class to and from within, and this is happening outside of a Teams distribute. So basically, the first one is correct, the second one is not going to work. And again, we had some compilers passing this, we had some compilers failing this. So we had to go back and figure out, which is the right version, which is the correct code. Another example is this particular example, where you have, there is a share, if you see, on both the shared clause as well as the map clauses. So then we eventually figured that, only the bottom one is correct, and you cannot just have a shared clause on the map as well as the shared clauses together. So these are very subtle, simple stuff, but you won't know where the code is failing if you have such, simple bugs in your code. For more results, definitely take a look at our website. CRPL is my group's name, cisudel.edu, so project's name, and we have compilers up to Clang 10 to 11, which is on Cori. We are yet to test Clang 10 and 11 on Summit, but the latest compilers available on Summit, and we have a table that has all the tests, passed or failed, and what versions of compiler that we are testing. So these results are up to date as of, I think we updated this on June 30th. That's a Parco journal we wrote, which is up to date. So far, as of, I would say 3-4 months ago, when the publication was made live. So it has a ton of information about how we go about, testing a particular feature. And that tells us, the number of passes, number of fails on different compilers, on different systems. So these are all not just on Summit, because you see the AOMP, which is an AMD compiler. So that's a local system in UD, which has AMD Vega cards. And so these numbers change, right? So every time we fix a bug, we go back and update the graph. This is about a few months old. But this kind of tells the vendors, what to look at, what not to. The acknowledgement that I have to acknowledge. And thank you very much. Without this, the project won't exist. We have a few minutes. I want to skip the next topic, but I do want to tell you about the training and education opportunities out there. So gpuhackathons.org, most of the information is there. So go take a look. The organization conducts or hosts, even virtually, hackathons across the globe. There are multiple opportunities for you to participate as mentors or participants. So feel free to take a look. There are events happening as we speak. And for instructors on the Zoom call, there are teaching kits, something that my student and I put together on new CUDA modules are the unified memory, dynamic parallelism, multi-GPU, and CUDA libraries recently added to the NVIDIA teaching kit. OpenACC teaching kits are available. It has quiz solutions, lecture materials, assignments. What more do you need? But yeah, so something for you to save your time. So yeah, so that's pretty much my last slide. Bottom line being, migration of codes, from platform A to platform B is not easy. And by now, I guess all of us would have realized that. There's just a lot that goes under the hood, and work is in progress. And we hope to, make Frontier as usable as possible for scientific developers. Thank you.
Thanks, Sunita. So interesting talk. And actually, we were also at our team. We were also looking into GPUs, migrating MPI onto GPUs, and we know how painful it is to get to access to new architecture and to get performance improved. So first of all, before we go into the discussion session, would you mind share the slides, because there are so many useful links? And
oh yeah, absolutely.
Okay.
I haven't gone to the Slack yet, which I will right after the Zoom call.
Okay, thank you. Yeah, so we know these links will be very useful for the attendees, like access to them. So I'd like to ask first the question.
Yeah.
And so, yeah, I actually, I'm surprised that there are so many experiences you shared to migrate applications from Summit to Frontier. So what's the most time-consuming part you consider? I mean, my understanding looks like just the cycle, right? Performance, both figure out, analyze the bottlenecks, and they optimize. But just to get a reasonable performance for one application to migrate to the new system. So what do you think that's the most time-consuming part?
I believe for the AMD systems, something that we're beginning to realize is we have to profile the code. Now, Nsight is not going to work on AMD systems, so what is going to be the profiler, right? There may be hint, wink, winks available, but the very first thing to do would be to figure out where is the performance loss on a new hardware device. So that's a starting point, and we have a faint idea, but we are waiting to actually try to find out that info on the GPU that will be in the system, right? And none of us know. I mean, I can't say much, but we don't know what it is going to be today, right? But we need to know. We need to be able to profile that particular device to be able to get all the details that we have from Nsight. So I would start from there, and then another challenge we have, so right now, is developing the robust backend for Alpaca. Both OpenMP offloading, and we have a HIP backend as well, and the OpenACC backend. So here there are several tickets opened with the vendors, and these are kind of almost new feature requests with OpenACC, especially. It's a new feature request that we're saying this code. It's a atomic feature that we required from OpenACC. It has a feature, but that feature was not good enough. So that needs to be ratified. That needs to be approved by the standard. It has to be a standard feature, right? It can't be a feature that works for only one compiler. So there's a lot of conversations, and then we go back to the scientists, which are the domain scientists. They'll be like, no, this doesn't mean anything to science. So then we are back to the drawing board, because often to get the best out of the GPUs, we create this massive problem size, and we see GPU utilization as 100%. But if you take the problem size and go to the physicists, they're like, oh, this doesn't make any sense to me from a science perspective. So how do you care, right? So there is that dialogue as well. While we want codes to run on the GPU, the codes have to make sense to the plasma physicists. So it's a fun project, but as you can see, there is a lot of pressure from every angle.
Yeah. I know the communication between different domains is kind of most challenging part for core design. Okay, so actually we are run a little bit behind of the time, but I think we get room to have one quick question. If anyone wants to ask, you can unmute yourself, just ask a question, I believe.
Yeah, thank you, Sunita, for your great talk.
Hi,
I have
Amkin.
a question for you.
Yes.
Yeah, so I was wondering, how do you validate your test suite, for some like upcoming future architectures, but not quite here yet?
Yeah, I know. Well, you have asked me a question for which I should talk for the next 1 hour. It's an excellent question. So we still go ahead and write a test for which there may not be an implementation. So there is a specification definition. So just with that definition, we write a test. But obviously, if there is no hardware platform, there is no way to check what we have written, right? So we go with whatever is available at the moment, but there is no guarantee that the next MI, XX, whatever it is going to be with AMD, the feature is going to work or not, right? So we test at the most available platform that we have, but there are tests in the trunk for which there is no implementation. So this is another conversation that we have with Oak Ridge and the OpenMP community, right? And but I mean, they have their reasons to want these kind of tests, because even if they cannot release the hardware to us, they have their hardware, right? So they can still take our test and go run it on their system and give us feedback. So whatever we can do to prepare a little bit in advance.
I see. Right. Yeah, thank you very much.
Thank you, Yamkin.
Okay, thanks, Yo and Sunita. So if you have more questions, feel free to post the question on Slack channel. Sunita will join the Slack channel very soon. And we also have the full slides on our website. And okay, so let's move to the next session, parallel computing on GPU. So for this session, we have 3 speakers, and we can extend the session for another 5 minutes in case we have more conversation to get this delay like bike. Okay, let's move to the first talk from now. The first talk is by Michael Torter about his paper, rumor has it, optimizing the belief propagation algorithm for parallel processing. So let me first have a brief introduction for Mike. I think Mike, now you can unmute your mic, and if available, please turn on your video so everyone can see your face. Thank you.
It is on.
Okay, perfect. Okay, let me. So, okay. So Mike is a recent PhD graduate of George Washington University. He specializes on optimization of HPC systems, including both cluster and the GPU applications. So, okay, now Mike, now is your turn.
Hi, I'm going to just give a quick overview of the paper and the slides presented for this workshop. So with this paper, what we did was we looked at the belief propagation algorithm, which is modeling how changes to the event nodes in a Bayesian network propagate throughout the entire network. These are usually used for things like hidden Markov models, neural networks, heat flow models, and so on. To basically to enable this kind of work, we made several key contributions. We have a refined input format that's scalable beyond the 100,000 node breakoff point for the traditional input format. Ours can be read line by line instead of having to be read entirely in memory before being processed. We support multiple approaches for processing the graph, both by node and by edge. And the node approach has more memory accesses, but fewer atomic instructions compared to the edge cases. We also have algorithmic and workload optimizations. We simplify the problem a bit with a single joint probability matrix instead of joint probability matrix per edge to reduce the memory usage. In addition, we support work queue optimizations to only do the work that's necessary, since most nodes converge very quickly. And we support belief propagation on both CPU and GPU platforms. although we did look at OpenNP and OpenACC. Due to the scheduler overheads in particular, we didn't really include them in the final contribution, which is Credo, which is using classifiers, particularly random forest classifiers, in a modeling task, which is classifying a given node based on the metadata that we derived from parsing the input graph on whether or not it's best suited for node or edge implementations. The random forest tree classifiers work best due to their ability to handle nonlinear relationships, handle small data sets, since we only have about 130 full examples, and deal with the covariant data in our features. And for our final results, we were able to get between 120x speed up on our benchmark platform and over 180x speed up on an unseen one. And I guess that's the quick overview of the project.
Okay, thanks, Mike. So everyone, if you have any question, please just unmute yourself and ask it. Okay, so Mike, I want to have my first question here. So it looks like this design is kind of interesting that it gets a better parallelism for this belief propagation algorithm. I do see that you compared CPU versus GPU, which means NVIDIA and CUDA versions, right? So in this paper, so have you worked on like any other, like evaluate this algorithm on any other GPU architectures like AMD, Intel GPU, and observe any interesting results there? Or you think the performance will be just portably good on those platforms?
We haven't actually evaluated it on other GPU platforms that, besides NVIDIA, it was just the Pascal and Volt architectures. So that would be an interesting problem. I mean, a lot of it is due to the amount of overhead in scheduling the threads. There's not much work being done per thread, but since there's so many threads being executed at the same time, that's where the performance gains would be best, especially for large graphs.
Okay, thanks. So that anyone has other questions, you can post, you can unmute yourself, or you can send a message on Slack. We can also forward it here.
So I assume the full presentation video is the one linked from the workshop website, right?
Yes, it's about 30 minutes, so quite a bit longer.
Mm-hmm. Sounds great. Yeah, thank you.
Yeah, it might be a little bit challenging for everyone to quickly understand the content because of the short pitch presentation. But we do encourage you to watch the full video on our website program page and ask any question if you like at the Slack channel after the live sessions. Okay, so I think, yeah, we got this presentation done. Thanks, Michael. And yeah, okay, so let's move forward. Okay, I would like to move forward to the next talk. So the next talk is by, actually this teacher says does not show the order name. So this is by Alex Sander Martis. He's going to present his work, Automated Partitioning of Data Parallel Kernels using Frankfurt compilation. So Alex, I see you are here. Would you mind unmute yourself and turn on your video? Thank you.
Sure. Can you hear me and see me?
Yeah, we can see you and hear you.
Perfect. All right. All right. So should I just start?
Yes, please.
All right, cool. So yeah, quick introduction. I'm Alexander Matz from the Heidelberg University. Or at least I was when I did this work. Now I work at a trading company. But as a quick disclaimer, to be fair to everybody involved, this work was done while I was with the Heidelberg University. All right, let's get into it. Let's start with the overall idea of the project. So what we wanted to do is create a software that takes as input a GPU application, a CUDA application, that is written so that it executes on a single GPU, which is kind of the default. And then the software should transform this application so that it executes on several GPUs, but also produces the correct results, of course. This requires some data flow analysis, and for this we use polyhedral compilation. Now I'd like to just illustrate this process on an example. So we start with the kernel code, which you can see in step 1. This is a simple 2D Jacobi kernel, which takes a 2D grayscale image, and then for each pixel in this image, it takes the average of the 4 surrounding pixels, and then writes that average into 1 pixel of the output image. So here you can already see that for each output pixel, we need several input pixels, and how many exactly and which ones we compute in the second step. So here we use a polyhedral library to analyze the memory access patterns of the code, and then we get a read and a write access in this case. Depending on the application, you can get different read or write accesses. And here you can see that the read access is a map from a thread with a 2D position in the grid representing a pixel to the 4 surrounding pixels. Please pretend that the box in the middle is not colored in, because that's not what the code is doing. But in the picture, I accidentally colored it in. And the write pattern is an identity map. Here we map just from the position of the thread and the 2D grid to the output pixel it is writing to. And so these patterns are stored in an abstract polyhedral model, which is a bit unwieldy to lug around in your application. And so in order to really make that usable for us, what we do is we generate code. And the code we are generating takes as input some partition of threads. So here you can see it's a rectangle of threads on the left side of the arrow. And what it outputs is the chunks of consecutive memory that this group of threads is accessing. In this case, it's a read access, and you can see that it mirrors these 4 surrounding 4 neighboring pixels for each of the threads in the input set. So now the code generation facilities of polyhedral libraries usually generate highly optimized code. So this allows us to very efficiently get a list of all the memory accesses of this group of threads, which is kind of cool. And so then once we have this information, what we do next is we transform the host code of the application, which controls the GPUs, copies data around, calls kernels, all this stuff. And we're doing several things, but what I want to point out here is the kernel transformation. So we're taking a kernel call in step 4. You can see above the arrow, you can see such a kernel call, and we translate it into something like the loop below the arrow. And the semantics of this transformation is that for each GPU that you have installed in the system, we first adjust the thread grid, so the threads that execute, to the ones that we want to execute on each GPU. Then we shuffle around all the data so that that each GPU has the data that it needs in order to compute its kernel and or to compute the correct results. And then afterwards, we update our internal model of where we think or of where we know the data is stored that each GPU computed. And so how do we do this like on an example, this like shuffling the data around? So let's assume that we're in iteration 4 or something. In step 5, let's assume we're in iteration 4 or something. So the data is already distributed on the GPUs. The GPU data of GPU 1 is the left half of the image. GPU 2 stores the right half of the image. And now we want to know what data does GPU 1 need that it doesn't already have. So what we do is we just overlay the read access of all the threads that GPU 1 is scheduled to execute. And then we look for all the data that it doesn't already have, which in this case is just the right halo of the image. So you can see this in the third image, you can see this line that is part of the data that GPU2 is holding. And that is the only data that we copy over. And this is pretty much the whole idea behind the project. And so we did this, and our findings are that this kind of automated partitioning works pretty well for fairly simple kernels where the data or where the memory access patterns are fairly simple. So in our experiments, we had speedups of between 6 and 12x on up to 16 GPUs on a single node. But in real life, most GPU applications kind of have fairly optimized kernels already implemented. And that makes it a little bit tricky to analyze the memory access patterns. And if we can't do that, then we cannot reliably know what data is read or written. Then this kind of breaks down. And so this is limiting the applicability a little bit. But like I said, for the cases where it works well, it works, or where it works pretty well. I think this is pretty much it for the overview of the project. I would like to yield.
Thanks, Alex. So does anyone have a question to this work? Okay. So I think there is a question on the Slack channel. Alex, if you are on the Slack channel, you can go ahead and look at that, but I'm going to read it here.
Yeah.
So the first question is, so it's by Ariel Rush. If Ariel, actually you can unmute if you can. And so I'm going to read this question. First, I'm wondering how the proposed approach compares to existing behavioral-based approaches focusing on code generation for multiple device systems. So he asked compared to related work.
Yeah, so there is definitely related work already existing. I think the main challenge that we have is that we used CUDA as an input language, which has kind of a loose coupling between the host code and the kernel code, and it makes the analysis of the overall data flow pretty tricky. And so I would say one of the main differences that that differentiates us from other work is that we have this dynamic memory tracker. So we don't try to statically predict all the data transfers that we need to do in advance. We kind of have like a mix between a runtime system and a static analysis and the code generation. But yeah, like I said, there is definitely similarities. I would say in spirit, probably the most related is that I can think of is distributed halide. Which also uses polyhedral compilation, but the halide programming language is a little bit stricter on the data accesses that you can have. So I think it's a little bit easier to manage the data dependency analysis. Yeah, I think this is my answer to question 1. And to question 2, what have been the main challenges faced while developing the proposed methodology? I think there's been a lot of challenges. I think one of the main challenges that we had was exactly that we were using CUDA, because it's not an open system, so we don't have access to the compiler. So we thankfully there is GPU-CC, which is an LLVM project that implements a CUDA compiler, which we were able to use for our purposes. But it still relies in large parts on the CUDA SDK. And so this using proprietary technology was pretty challenging. And I would say maybe really the biggest challenge that we had were existing applications. So if you look at the paper, the applications that we were using to evaluate this approach are ones that we have written ourselves. Because so we were looking at existing benchmarks, and they're already typically so highly optimized that you when you build them back, you kind of end up at the applications that we were using. And so I think the main challenge is making this robust enough for real life use cases. It's like this is a prototype that works just in a limited scope, and I think there's a ton of engineering effort involved in making this applicable for a wider variety of applications.
Okay, thanks, Alex, for answering those questions. I do want to have a following up question for just for continue the discussing about the challenges for this work. So to extend it to cover the other applications, let's say have different memory access patterns. So
Yeah.
So are you thinking the main work will be engineering work, like developing those patterns in this software, or there are something else we have to do to extend it?
Yeah, that's a really good question. So the cool thing about polyhedral compilation is that we don't have to implement particular pattern. So I used the 2-dimensional Jacobi as an example, but basically every more or less like reasonably simple static access pattern can be represented. So basically, if your memory access patterns are a linear function of your thread index, then you can model it usually pretty well with linear constraints on these accesses within the polyhedral model. So everything that satisfies this criteria should work pretty well out of the box. Thankfully, this work is pretty much done by polyhedral libraries already. What I think, so if one would want to extend the coverage of this approach, then I think we would have to implement more edge cases, because there's certain patterns that you see showing up again and again in GPU codes. Tiling, for example, is one. And so I think it wouldn't, so if you would add special support for certain tiling patterns, I think that would increase the coverage of this approach.
Thanks, Alex. Interesting talk. So yeah. So any other questions? Okay. I think we can move forward to the next presentation. Thanks, Alex. And as we mentioned, if you have any questions afterwards, feel free to post on the Slack channel. Okay, let's move forward. Okay, so now we are going to have the third paper presented for the second session. So the third paper, again, it does not show the order name on the pitch slide. So okay, the third paper is from Zahar Kaharaj Monfaraj for his work BSRNG, a high throughput parallel bit sliced approach for random number generators. So Zahar, are you available online now? I'm not sure if I see on the Zoom participant list. If you are here, can you please unmute yourself and turn on your video? Let's wait for a few minutes. Actually don't get contact. I actually don't get update from the author, so I'm not very sure if.
Yeah, is it because we are ahead of schedule?
Yeah, probably, but it's 4 minutes ahead of schedule, so.
4 minutes, okay. So this talk is supposed to be from 2:30 to 2:45 Eastern time.
Yeah.
Yeah.
Let's wait for another 4 minutes, see if the presenter will show up.
Great. Thank you.
Okay, so let me repeat again. So we are waiting for this presenter for the third paper at the session 2. The paper will be BSRNG, a high throughput parallel bit slice approach for random number generators. So if any of you will be the presenter for this paper, please unmute yourself and say hi to everyone. Yeah, so, okay. It looks like we missed this third presenter. It's unfortunate we don't get any updates from the others. So I would suggest that because this is a last paper for session 2, and we posted that the last invited talk will start from 2:45 p.m. EDT, which will be 15 minutes from now. I don't want to change the schedule because I know people will just join the workshop maybe for some of the talks they are interested in. So I suggest that we take a 15 minutes break. We come back at 2:45 p.m., which is 15 minutes from now. And we can start the third video talk by Akhil from NVIDIA. So how does that work? Okay.
Sounds great. Yeah.
Yeah, thanks. So, yeah. Okay, let's move my slides to the last invited talk. So we know we will start from there after 30 minutes. Okay. So see you guys in 50 minutes. Okay.
Okay, yeah.
We can see the screen. Thanks, Nathan. Okay, so now I think we get started for the third invited talk given by Akhil. Before we start, I would like to have a brief introduction for Akhil. So Akhil is a senior software engineer at NVIDIA. He completed his PhD in computer science from University of Illinois at the Urbana campaign in 2015. His research interest lies in high-performance computing runtime systems and applications, parallel programming, scalability, and stochastic optimizations. At present, he is the lead developer of the NVShman, that is a parallel programming library for NVIDIA GPU clusters. So, Akhil, now it's your turn.
Okay, thank you, Min, for the introduction. So, good afternoon, everyone. I'm currently a senior software engineer at NVIDIA. And like Min mentioned, I have a background in high performance computing. I did my PhD in HPC. Currently, I am the lead developer of NVIDIA's NVShman parallel programming library. So NVShman is it's a very interesting library that allows the programmer to do communication across GPUs right from within the CUDA kernel. But before we get into doing communication from the CUDA kernels or from the GPU device, let me just tell you about what are the disadvantages of doing CPU initiated communication. So in a typical programming model, in a heterogeneous system with CPUs and GPUs, the compute is done on the GPU, and then the CPU would wait for the compute kernel to complete, and then the communication is issued from the CPU. This typical way of doing programming is shown on the right side of the slide. And there are several disadvantages to this approach. First of all, like in every iteration of the application, the kernel has to be launched, and then you have to synchronize for the kernel to complete. And this launching and synchronization adds to latencies on the critical path. And the second disadvantage is that you cannot overlap computation and communication. So it is possible that to overcome these limitations in some scenarios, the programmer can try to hide these latencies by having an increase, by having a more complex code. However, that leads to significant increase in the complexity of the code. And if you don't try to hide these latencies from the critical path, then that leads to limitations in the strong scaling of the application. So now what we are proposing in this is to do communication from the GPU itself. Therefore, both the compute and the communication happen from the CUDA kernel, and it is shown on the right side. There are several advantages of taking this approach. First of all, the kernel launch and the synchronization latencies, those can be eliminated from the critical path, since now both the compute and communication are happening from the GPU. Now that both of these things are happening on the GPU, the programmer has the option to overlap the computation and communication. Also, given that multiple CUDA threads run simultaneously, communication latencies can be hidden because of a simultaneous multi-threading. And finally, also, it is much easier to express the algorithms when communication can be inlined with the computation itself. So we can get an insight like having this kind of programming model, it would improve performance while also making it easier to program. Now, talking about NVShman. So NVShman is NVIDIA's programming vehicle to do GPU-initiated communication. In simple terms, NVShman is an implementation of OpenShman standard for NVIDIA GPU clusters. The NVShman communication and synchronization API can be invoked from CPU as well as from the GPU. Now, for those of us who have not heard of OpenSHMEM before, OpenSHMEM is a PGAS or partitioned global address space programming model. The global address space is distributed symmetrically across GPUs. It is shown in the green boxes in the diagram. Objects can be allocated within this symmetric memory using NVSHMEM malloc API. And then these objects are then remotely accessible using OpenSHMEM's one-sided communication API. One thing about OpenSHMEM is that you can access remote memory using reference to symmetrically allocated local objects. This makes it easier to write programs using OpenSHMEM. Now, in addition to remotely accessible memory, an application can always also allocate private memory that is not remotely accessible, and that memory can be allocated using CUDA malloc. We'll use this term PE often in this presentation. PE in the context of OpenSHMEM is basically equivalent to a rank in MPI. Now, as far as the current status of NVSHMEM is concerned, we recently released NVSHMEM 1.0.1 in June this year. And before that, we had done several early access releases of NVSHMEM. You can always download NVSHMEM library from this NVIDIA link. Now this NVSHMEM API, it is based on OpenSHMEM 1.3 standard. And as we are making newer releases of NVSHMEM, we are incrementally adding more and more API from OpenSHMEM 1.4 and OpenSHMEM 1.5. In addition to OpenSHMEM API, NVSHMEM library also has NVSHMEM specific extensions to the OpenSHMEM API. For example, for GPU initiated communication, we have thread block or warp level extensions to the OpenSHMEM API. These API are invoked collectively by a group of threads, and NVSHMEM can leverage these threads to implement the API. We'll talk more about these API in a short while. In addition to these thread and block versions of the API, we also have stream-based API that allows the programmer to enqueue a communication operation onto a CUDA stream. Again, we'll talk about stream-based API as well in a short while. Now, as far as the implementation features are concerned, NVSHMEM supports GPUs that are multiple GPUs that are connected either via NVLink or PCIe or InfiniBand or a combination of these. NVSHMEM also has support for both x86 as well as Power9 CPU architectures. And it is also interoperable with MPI and OpenSHMEM. So let us, to get an understanding of the API, let us take a quick example of a stencil application that uses NVSHMEM from the CUDA kernel. On the left, we have a 2D array that is decomposed along the Y dimension. And it is distributed across PEs. Each CUDA thread would basically just, in this particular example, each CUDA thread is just calculating one cell in the array. And if it happens to be a boundary cell, it also sends it to the neighboring GPU. To do the communication, we are using NVSHMEM float P API. This API basically just writes a single float element to the remote GPU. When the neighboring GPU is connected via NVLink or via PCIe, this API just translates into a single store instruction. And as you can see, this API is making it possible to allow very fine-grained communication because these are single element transfers. And this kind of communication maps very well to NVLink fabric on NVIDIA's DGX systems. Now, these slides talk about the thread block extensions of the put API. Put API in OpenSHMEM is basically used to send an array of elements. in the thread block extension of the put API, all the threads in a thread block, they call that API with identical arguments. What happens is, like, if the GPU, target GPU is connected via InfiniBand, NVSHMEM can issue a single InfiniBand operation to send the entire array of elements. And that is much more efficient than doing single element transfers over InfiniBand. Now let us talk about doing synchronization across GPUs from the CUDA kernel. So in the stencil application, GPUs, they need to synchronize with each other in each iteration, and NVSHMEM makes that possible by allowing synchronization API as well from the kernel. Now, as you notice here, this particular piece of code here, it's a multi-step kernel instead of a single step kernel that we saw in the previous slides. And within the same kernel, we are doing both communication across GPUs, as well as we are also able to synchronize the GPUs from the kernel itself. Now, the final API extension that I want to talk about is the stream-based extensions. In some applications, it is not possible to, it is not optimal, actually, I should say, to move the entire communication and synchronization into the kernel. So one example of such a scenario is when doing grid level synchronization inside a kernel is more expensive than doing a new kernel launch itself. And another scenario is when there are several different compute kernels that are computing on different data sets, and they need to be synchronized together. So in such instances, one can use these CPU initiated operations that can be enqueued onto a CUDA stream. And this makes it possible to do fine-grained communication inside the kernel with coarse-grained synchronization across GPUs using on-stream variants of the API. Okay, so now what we'll do is we'll take a quick look into some of the implementation features of NVSHMEM. So like I mentioned before, there are two types of GPU connections that NVSHMEM supports. Ones that are peer-to-peer connected via NVLink and PCIe, and others that are connected via InfiniBand. For peer-to-peer connected GPUs, what we do is we use CUDA IPC to map the memory of these peer connected GPUs onto the virtual address space. And once the memory is mapped, the put and get API is basically just simply translates into load store instructions. And load store instructions when this API is called from the device, and if you call the put and get APIs from the CPU, then you can use CUDA memcopy API to do the transfer. So the second type of connections is when the GPUs are connected via InfiniBand. Currently, the way we implement a communication across InfiniBand connected GPUs it is by reverse offloading the transfer requests back to a proxy thread that is running on the CPU. This reverse offloading of the InfiniBand requests from the GPU to the CPU happens through some lightweight signaling mechanism that we use within NVSHMEM. That mechanism, it tries to avoid memory fences to make it efficient to communicate between CPU and GPU, and it does that by using the single copy writes that contains both the synchronization, both the data as well as the synchronization flags. So this was about how we implement communication across peer-to-peer GPUs and across InfiniBand connected GPUs. Now we'll talk a little bit about the performance of the put API when the GPUs are connected via NVLink. So on this plot, you can first see this gray line, which is like the ideal performance that you can expect from a that you can expect, because it is basically performance of bandwidth of directly using the stored instructions on NVLink. And the blue line shows the performance when using when using the NVISH Put API. And the difference in the performance is because of two reasons: because of the API function called overhead, and because of the address calculation that is required before we do the store. So we were able to overcome this gap by implementing the Put API inside the NVISH header files instead of having them implemented inside the library. By that, we can see we get the performance that is shown by the orange line, and it is very close to the optimal performance. Like I mentioned before, NVISH is interoperable with MPI and OpenSHMEM. This makes it possible for existing applications to port part of their code to NVISH instead of having to port the entire application. The first code sample on the left shows how NVISH library can be initialized using MPI communicators. And the one below shows initialization of NVISH library using SHMEM default context. One more thing that that is notable about NVISH is its interoperability with CUDA graphs. Before that, let me give a quick intro to CUDA graphs. CUDA graphs is basically a relatively new feature that was introduced in CUDA 10.0. It allows the users to express various CUDA API calls as well as kernel launches as nodes in a graph. And then you can also express dependencies across these nodes. So having the knowledge of the graph makes it possible for the CUDA runtime to have more efficient execution of the graph because it can optimize launch overheads as well as do some workflow optimizations. So that was about CUDA graphs, and one of the notable features of NVISH that it is interoperable with CUDA graphs as well. What that means is that nodes in this graph can be kernels that use NVISH API, and the nodes can also be the on-stream operations supported by NVISH. So this is a notable distinction as compared to distinction from existing CUDA-aware MPI libraries that do not have support for CUDA graphs as of today. Now let us look at some interesting performance results. CUDA, so CUDA spelled as QUDA. It is basically a very popular GPU-enabled quantum chromodynamics library, and it is used by several popular packages like Chroma and Milk. Chroma takes about 15% of the total Titan supercomputer usage, and at NERSC, CUDA applications like CPS, Chroma, and Milk, they constitute about 12% of the total application hours. CUDA is a latency-bound application, so and NVISH enables better strong scaling in CUDA by using GPU-initiated communication and synchronization. So we get up to 1.4x speed up on a single DGX. Sorry, 1.7x speed up on a DGX2 system, and up to 1.4x speed up on a DGX SuperPod with 1024 GPUs. Now let us look at performance of Jacobi Mini application. This plot shows its strong scaling performance on the Summit supercomputer at OLCF. The Summit supercomputer has 6 GPUs per compute node. As Jacobi is strong scaled from 1 node to 64 nodes, parallel efficiency with NVISH is significantly better than with MPI. As you can see, at 384 GPUs, NVISH is about 4 times more efficient than the MPI version. Again, this is accomplished by doing communication and synchronization from the GPU itself. The next application is Livermore's big artificial Neural Network Toolkit, or LBAN. It implements parallel convolution using MPI, Aluminium, and NVSHMEM. Aluminium is basically it's a generic interface to HPC libraries like MPI and Nickel. And in case of MPI and Aluminium, the Hello exchange in this parallel convolution kernel is implemented using CPU side sends and receives. But in case of the NVSHMEM version, it uses the on-stream and GPU initiated API provided by NVSHMEM. These performance results were measured on the Larsen supercomputer at Livermore. Each of the nodes in Livermore on the supercomputer has 2 Power 9 CPUs and 4 Volta GPUs per node. And you can see that NVSHMEM provides clear performance benefits over MPI and Aluminium, and particularly at higher GPU counts. Okay, so we've talked about performance so far. I also wanted to give a brief insight into the programmability with NVSHMEM with the help of example of the COCOS programming model. COCOS, it's a parallel programming model that provides performance portability across the HPC systems. It is primarily an on-node programming model. However, NVSHMEM was recently used to implement an extension of COCOS to support data structures that are similar to global arrays. This removes any need to program explicitly communication between GPUs using MPI. And what it led to was that it led to significant reduction in the code development and tuning effort. And all that the programmer had to do was to change the data structure type from local arrays to NVSHMEM backed arrays while still using the same single GPU code. And as reported by the developers of this code, they said that the entire COCOS plus NVSHMEM implementation required less lines of code than just the pure communication routines of the MPI variant. And the overall size of the code was about 6 times smaller. So this is my final performance slide. It shows benefits of NVSHMEM using a synthetic benchmark. So to understand these results, just consider an application like Jacobi solver, in which there is a collective operation, for example, all reduce or a barrier collective operation after the compute kernel. So if you have to write this thing using MPI, what we would have to do is after the compute kernel, we would have to do a CUDA device synchronize and then do the MPI collective operation. This is to ensure that the compute kernel is complete before we do the collective operation. In case of NVSHMEM, the collective operation can just be enqueued onto the same stream as the compute kernel. And since the two are on the same stream, they would be executed in sequence, one after the other. And therefore, by doing it like that, we avoid the overhead of CUDA device synchronize. Now, this plot shows the benefits of NVSHMEM over MPI at different GPU counts of a DGX2 system. Okay, so finally, something about what we are working on right now and we plan to work on in near future in NVSHMEM. Right now, we are working on implementing newer features of OpenSHMEM standard, for example, Teams API and the Context API. These are some of the new features that were introduced in recent OpenSHMEM specs.
Did we lose the feed?
Yeah, I think Akio lost his connection. Okay, back.
We are also experimenting with GPU verbs transport GPU verbs transport is basically in contrast to what we are doing today in NVHMEM. What it does is the GPU threads themselves post the InfiniBand commands to the NIC rather than having to reverse offload them to the CPU. So we are experimenting with this transport as well. We are also looking at automatic coalescing of fine-grained transfers for better efficiency over InfiniBand. And finally, we are also looking into supporting non-contiguous data transfers. All right, so that's all that I wanted to talk about NVHMEM. So I can take any questions while you go over these points that I've already mentioned.
Thanks, Akhil, for the interesting talk. Yeah, I think we have one question from Michael Porter on the Slack channel. So if you are on the Slack channel, you can read it. And I can also repeat it here. Actually, Michael, if you can unmute yourself, you can ask a question here too.
Yeah, Caleb, that's a very interesting talk. I'm particularly interested in how applicable NVHMEM is for like graph analytics, like pair training or all pairs shortest path.
Yeah, it really depends on the algorithm itself. I have not worked with these applications, so I cannot tell you, but we have, prior to me, there was some work on using NVHMEM with a breadth first search, and I can share some results of that. We have some performance results with breadth first search. So I don't know, we'll have to, I'll have to see what the
We have problems with his connection.
So Akhil, probably you want to repeat the last sentence because we didn't hear it. The connection was not stable.
Oh, can you hear me now?
Yeah, now we can hear you. Can you repeat the last sentence?
So I was saying that all we have, as far as graph applications is concerned, we have done some work on porting breadth first search benchmark to NVHMEM, and I can share some results, performance results from that. But it really depends on the communication pattern of the applications that Michael mentioned to see if they can benefit from NVHMEM or not. So I would, before commenting, I would really like to know what exactly is that application.
Well, I mean, it might be applicable for like the research I'm doing with belief propagation, but that one had more like non-uniform memory access patterns.
I see. So, yeah, actually we have some ongoing work on non-uniform memory access as well. But I do not have performance results right now to talk about that. Yeah.
Do you still
Michael,
need to
there was
share your screen, or should we stop your sharing?
I think the screen is still being shared.
Should we stop it?
Should I stop it?
Yeah.
Yeah, we can stop it. Probably then the connection will get better.
And we can see everybody.
Yeah.
Michael, there was another part to your question. You asked cases where the graph doesn't fit in a single GPU's memory. And I think that's a particularly good case for where NVHMEM is helpful, right? In the sense that it allows you to access the memory of multiple GPUs that are working together in a cluster.
Yeah, I mean, that was one of the issues I came across is when trying to go to multiple GPUs, the performance went down like a rock.
Yeah, I mean, it's a challenge when you, particularly if you have a system that combines both NVLink and InfiniBand. I don't know, maybe Akhil can speak a little bit to some of the things that are happening in that space with NVSHMEM.
So you're talking about performance drop when going over InfiniBand?
No, I mean, that was just trying to, it was in a preliminary analysis, so we weren't using anything that advanced. I mean, we're just testing things out.
Mm-hmm. So what we are trying to do is for non-uniform access, it would work fine over NVLink connected GPUs, but when going over InfiniBand, we would try to coalesce or aggregate those requests into a single we would try to aggregate and then make a single request to the target GPU and then receive all the requests back again as a single message instead of having to do fine-grained transfers of data that is connected data over InfiniBand. So so that's the effort that we are going to put, is to be able to aggregate these random requests into single request and make efficient use of the InfiniBand.
Interesting. Thanks.
Actually, I do have a follow-up question. It might go into a little bit deep of the internal implementation of the enrichment. So it's also the same like a topic about irregular memory access. I have read a paper. I think it was published by AMD guys, and they also have similar GPU initiate support by using OpenSHMEN interface. They did mention one big problem for GPU communication, GPU to GPU communication, is that the GPU they NIC, or for example, the InfiniBand adapter on the remote process cannot flash the remote GPU's memory cache. So for example, if you do a put plus a quite on the origin process, the quite cannot somehow be performed by the InfiniBand adapter automatically, and from the NIC side to flush out the GPU memory, so the GPU memory will be visible, the updates can be visible to other GPU or other CPU on that remote process. So they did mention that problem in their paper. I'm not sure if NVIDIA CUDA has a similar issue.
Yeah, we do have a similar issue. That is about right-to-right ordering. So what we do is we try to reduce the impact of that by flushing PCIe during the atomic operation. For example, after doing a put, you would synchronize with the target PE to tell that the put has been completed using, let's say, OpenSHMEM's atomic API. The atomic API itself, the implementation of that API itself would flush the PCIe on the target GPU. So that when the target GPU waits on the atomic variable, and by the time it returns from that wait, the flushing has already happened. So the latency is hidden, but it nonetheless exists. We have to flush the PCIe. Yeah.
Okay, thanks. Do we have any more questions for this, for the enrichment talk?
Yeah, I have 2 questions.
Sure.
We have time to discuss.
So please make it as a short question.
Okay. Yeah, one question is more for clarification. So yeah, I hear you show a couple of slides for comparing the results between MPI implementation and NVSHMEM implementation. So my first question is, yeah, for that MPI implementation is pure MPI, or is MPI plus CUDA, some hybrid?
Yeah, those are MPI plus CUDA implementations. Those are optimized MPI where we try to overlap computation and communication while using CUDA kernels. So those are optimized MPI implementation of those applications.
I see. Okay. My second question is, yeah, so for NVSHMEM, when you guys implemented, are there any GPU caching involved? And if there's caching involved, is there any consistency, cache coherency issue?
Uh,
Or the
so I mean, any coherency issue across threads would be handled through any of the synchronization API itself. I am trying to, yeah, NVSHMEM itself does not do any caching. So there is no coherency issue from that point of view. Yeah, I don't know if that answers your question or you had something else in mind.
Okay. Yeah, that's fine. Yeah, thank you. I just want to check your opinion for that.
Thanks, Aki and Yong. I want to remind you again, if you do have more questions, not only today, I think for the entire week for the ICPP, you will be able to access to P2S2 channel on Slack and always ask a question there. And if any of the others does not see the questions, we can forward. So yeah, please use this resource. Thanks, Aki, again, to give me the interesting talk.
Thank you. Thank you for the invitation.
So I think we are mostly at the end of this workshop. I would like to thank you everyone again for participating in this workshop today. The virtual workshop is kind of challenging and interesting to us. And we had a great conversation here. And I would like to thank you all the presenters again for their interesting talk and the conversation with the attendees. And at the end of the workshop, I do want to mention a few things as a closing remark of this workshop. The first thing is that next year, 2021, we will still have P2S2. We will still work with ICPP 2021, and we heard that it will be held at Chicago next year. So hopefully we can see everyone physically next year. And so the website for P2S2 2021 is not up yet, but we will use this link. It's quite consistent with the previous P2S2 workshops. So you can probably get there and see if we have any updates. We usually will share with information with the past authors and some attendees. So we will get updated from there too. Okay. The next thing is about the review process. So every year we are trying to get a little bit of refreshment for the program committee. So we will have a similar program committee as this year. And we want to make a little bit of refreshment. We encourage early career researchers to join us if we are interested in programming models, runtime systems for high-end communication. So as you can see, we have many interesting topics covering CPU, GPU, other accelerators like FPGA, and even RISC applications, platforms. So it's quite interesting. If you are interested in contributing to review the papers, please email us. You can find our email on our website. But I do want to have a small note that to be involved in a program committee, we require you to get a PhD degree. So please have signed, because we get some contact from some PhD students, but unfortunately we cannot have a PhD student in the committee because we want to make the review process to be fair to all others. Okay, so the review will still have 4 to 5 reviews for each paper. We will ensure that the review will be high quality, and it will be discussed at the PC, telecom, or online to make sure we have fair and decent reviews, feedback provided to all papers submitted to us. So let's get involved in paper submissions, in workshop attendance, and advertising. See you next year, hopefully at Chicago physically. Thank you everyone for attending the workshop today.
Thank you, Min. Yeah, play this clapping sound on behalf of the audience.
Yeah, okay. Have fun for the other sessions at ICPP this week. And if you do have any question to ask or to any others and the presenters at the P2S2 workshop, please send a message to Snack. Okay. Have a great day, everyone.
Thank you.
Bye-bye.